Hello everyone. Welcome to Cloud on Air Live if you're just joining us, and welcome back if you were with us for the last session. Next up, we're going to be talking to Theo Shamley. Theo is a solution architect who's based out of our Paris office. He's going to be telling us a little bit about Spinnaker and CI/CD. How do you adopt those processes for getting continuous delivery so you're always out there building code and getting stuff out to customers fast?
Hi, as Tom just said, I'm Theo. I'm a solutions architect, and as you can tell by my accent, I'm a French solutions architect. So today I wanted to talk to you about continuous delivery, and more particularly about Kubernetes and Spinnaker. So that everyone knows what we are talking about today, we'll go over Docker and Kubernetes first, and then Kubernetes Engine and Spinnaker, and we'll finish with a demo and a Q&A session. We have a team of moderators on standby, so you can ask your questions. I will answer some of them at the end of this presentation, and the moderators will answer the others. So here are a few sentences I'm sure you have either said or heard. We are coming from a world where development and operations were combined, or not combined actually, into a big mess. Programmers want to program, but they usually spend too much time deploying and configuring environments. On the other side, operators, what they want is to keep the applications that they are running stable. And to do that, they put constraints on the deployment process in order to control it and to lower the uncertainty. But those constraints actually are slowing the deployment process, and they're slowing the whole software development process. So, containers are the first part of the solutions to our problem. Docker is a software by the company of the same name, and this software actually makes containers easy. So let's dive in a little into Docker and containers. The idea of a container is actually not new and has been in use at Google for over a decade. So let's go over the differences between a container, a virtual machine, and a bare metal server. With a bare metal server, you have to manage everything down to the hardware. This management changes from one host to another, and it's actually quite complicated to do well. With a virtual machine, you manage everything down to the operating system. But if you don't exactly have the same operating system configuration, your application is not guaranteed to run. Finally, with containers, you manage only your application and its dependencies. And it will run exactly the same way as long as you have a Docker-compatible operating system. And you won't hear your developers or yourself say it ran fine on my machine anymore. So, the beauty of Docker containers is that they are practically invisible to the application. And most applications will run as is inside a container. So in the end, the work to make an application run inside a Docker container is actually very minimal. One important best practice about containers. They are made to run a single process, and that's maybe the biggest difference with a virtual machine. This way, by running a single process inside a container, you can have the same life cycle for both your process and your container. When the container starts, so does your process, and when your process dies, so does your container. What it means in reality is that for a standard Nginx, PHP, MySQL stack, you'll end up with 3 containers and not have them in a single machine like maybe you're used to with virtual machines or bare metal servers. So, containers are nice because additionally to being a great runtime environment, because they ship everything with your application, they're also a packaging system. So once you have your application inside a container image, you can ship and run this exact same image everywhere you need. And when I say exact same image, I mean bit by bit the same image. So just one point to be clear about the vocabulary. What you ship is a container image, and the container itself is an instantiation of this image. So you can have many containers that are running from the same image. On the right of the slide here, you can see an example of how to build a Docker image. you have instructions in a file called the Docker file that describe how the image is to be built. So in this particular example, we're building our image from the latest Debian official Docker image. We're running a couple of apt-get commands, and then we're saying that by default, this container should run the nginx command. As I mentioned previously, Google has been using containers, but not Docker, for a long time internally. Google has actually been the company that has submitted the Linux kernel features needed for containers inside the Linux kernel. And containers allow to abstract the underlying infrastructure. And this particular abstraction enabled Google to grow its workloads 10 times faster than its operation teams, which was crucially needed for the size of Google's operations. But in the end, having a container technology is not all. So when you start to play around with containers and you want to push them to production, you rapidly start to encounter some of those problems. The first one is, well, where should I run my containers? How do I configure the virtual machines where I want to run my containers? Another classic one is, how do I get my containers to talk to each other? Because they're so nimble and they can jump from one machine to another. And how do they find each other? Because containers usually have a very short lifespan, their management is quite different than what most people are used to. And so we must manage them differently. This is where Kubernetes comes into the picture. Kubernetes is sometimes abbreviated KATE, K8S. So what is Kubernetes? First, it's a container orchestrator. You can give Kubernetes a pool of machines and ask it to run containers on those machines. If a container or machine goes down, it can move the workloads as needed. It can also horizontally scale your workloads and do a lot of other things. Second, it's declarative. This is very important. You don't have to describe to Kubernetes how to reach the state that you want. You just have to describe to Kubernetes what workloads you would like, and Kubernetes will by itself figure out how to reach this state. Third, it's an open source project. Kubernetes is not a proprietary system, and you can run it wherever and however you like. It provides a great abstraction to whatever your infrastructure is. A lot of major companies are backing Kubernetes by committing to the open source project. And finally, Kubernetes comes from Google. Google uses a tool called Borg internally to schedule its own containers, and Kubernetes has the same principles and architecture. It benefits from years of experience on how to run containers at scale at Google. Google actually runs more than 2 billion containers per week. So let's go over some Kubernetes concepts that we'll need later in this presentation. The first one is the concept of nodes. And a node is basically the machine that is hosting the cluster. So one Kubernetes cluster is composed of many nodes. And those nodes can either be virtual machines or bare metal servers, or a mix of the two if you want. The next concept is the concept of pod, and this is maybe the most important concept. A pod is the smallest object that you can have in Kubernetes. And a pod is basically a bunch of tightly coupled containers that are going to be scheduled on the same host, on the same node, and that are going to share some characteristics such as their IP address. A good example of why you would want more than one container into a pod is, let's say that you have a pod with an application and that this application needs a caching system such as Redis or Memcache. Then you can have inside the same pod both your application and Redis, for instance. The next concept is the concept of deployment. A deployment is a way to say to Kubernetes, create this particular pod a given number of times. And if one crashes, then restart one. The deployment also implements some very nice features such as rolling updates. So if you want to update your application, you update the deployment with a new Docker image, and Kubernetes will by itself do a rolling update of your pods. The next concept is the concept of services. So a service is basically a load balancer, and it can be both internal to Kubernetes for one pod to talk to other pods, and external by piloting a load balancer on the underlying infrastructure. In the case of Google Cloud Platform, this is a Google Cloud load balancer. And it also has some nice features around service discovery using DNS. And finally, the last concept that we need is the concept of label. And this is a bit different because this is not an object in Kubernetes, but every object in Kubernetes has labels, and those labels allow you to organize your objects. So one good example of the use of labels is the way that services work. So if you want to load balance some traffic to several pods, you're going to put the same label on each of those pods, and then configure the service to load balance the traffic to all pods that are bearing this label. So, to sum up, here is the internal architecture of Kubernetes. You have one or several master nodes where the API server is running. This is where most of the scheduling decisions are made. On each node, you have an agent called the kubelet that keeps in touch with the master node. When needed, the master node can instruct the kubelet to create or destroy some containers. And the kubelet will do that by communicating with the container runtime, which is, in our case, Docker. And Docker will create containers that are grouped into pods. And each pod is part of a larger construct that defines how it is scheduled. So here we have three different constructs: a daemon set, a replica set, and a stateful set. And each of those have different features and how the pods are scheduled. So for instance, the daemon set will make sure that there is one pod on every node. This is mainly useful for logging or monitoring or those kind of stuff. And finally, we have services that load balance the traffic both inside and from outside the cluster. For inside the cluster, this is done with IP tables, and from outside the cluster, this is done by piloting some external load balancer and routing the traffic to the right place. After the previous slide, I bet a good number of people are telling themselves that this sounds very, very complicated. And they would mostly be right. Kubernetes is actually a very complex system with a lot of moving parts. As installing, running, and upgrading a Kubernetes cluster is a lot of work, and you need to be very experienced with it to do it well. Google has its own answer to those problems, and it's called Google Kubernetes Engine, or GKE. So let's go over the features of GKE. So let's go back to our diagram. Kubernetes Engine is, well, that. Basically, Kubernetes Engine manages everything related to a Kubernetes cluster. Kubernetes is a complex system, and at Google we think that you shouldn't have to worry about how to run it. We think that what you probably want is to run the applications that are critical to your business. And Kubernetes Engine is here to allow you to do just that. So here are a few features of Kubernetes Engine. Kubernetes Engine is running a stable, vetted, and modern release of Kubernetes, which is coming straight from the open source project. And you can also try the alpha features of Kubernetes by running an alpha cluster. Everything is managed by Google, both the masters and the nodes. And so those are managed by Google and also upgraded by Google. And because everything is managed by us, you also have auto-scaling. So if your cluster is too small at one point, you can enable auto-scaling and it will grow as needed. You have some regional clusters that are spanning several geographical zones to improve availability. And finally, the nodes are running a specific operating system that is built and maintained by us. It's called the Container Optimized Operating System. And it's security hardened, and it does in-place upgrades. Because Kubernetes Engine is actually built on top of GCP, you benefit from all the other advantages of Google Cloud Platform. Mainly the advantages from Compute Engine, with very performant underlying virtual machines, with very fast boot times, with an awesome global load balancer, and with accelerators such as GPUs and tomorrow TPUs. And finally, Google Compute Engine has a very friendly pricing, and that is reflected with Kubernetes Engine. So you can have per second billing and sustained use discount. You can have preemptible machines for non-critical workloads, and you can specify your own custom machine types. And finally, Kubernetes Engine. In Kubernetes Engine, the masters are free of charge. So Kubernetes implements a lot of features, such as rolling updates or auto-healing. However, implementing some more complex deployment patterns is probably a good idea for large companies or even small ones, but with very specific needs. For example, how do you test a new version of your application directly in production? Kubernetes allows you to do that, but you have to implement the logic yourself. Kubernetes is a place where you run your application. It is not a replacement for your continuous integration and continuous deployment toolchain. So for that, let me introduce you to Spinnaker, a tool dedicated to continuous deployment. So what are some characteristics of Spinnaker? First, it's a multi-cloud tool. Spinnaker is able to manage your deployment on Google Cloud Platform, but also on other cloud providers. And within GCP, it integrates with several products: Google Compute Engine, Google Kubernetes Engine, and Google App Engine. Second, it's open source. Like Kubernetes, Spinnaker is not a proprietary software, and you can run it wherever and however you like. Third, Spinnaker comes with a lot of built-in deployment strategies, such as blue-green deployment or canary deployment. In the demonstration later, I'll show you the canary deployment. You can implement your own strategy, but more often than not, you don't actually need to. And finally, Spinnaker has originally been created by Netflix, but it is now heavily backed by Google. And we at Google make sure that all the integrations for Spinnaker, for Kubernetes, and our other products are here and that they work. So I said that Spinnaker can deploy to Compute Engine, Kubernetes Engine, and App Engine, but those are three very different products. So Spinnaker does different things with each. Let's first take a look at Compute Engine. If you use Spinnaker with Compute Engine, Spinnaker will be able to bake, that is to create new virtual machine images and deploy them by doing a rolling upgrade, for example. App Engine is a platform as a service, so it manages most things by itself. But Spinnaker can still help you automate your deployments. For example, Spinnaker will be able to deploy a new version of your application to only 10% of your users, wait for human confirmation, then complete the full deployment. And finally, with Kubernetes Engine, Spinnaker can help you implement those advanced deployment methods, such as blue-green, directly inside Kubernetes. Okay, now let's map out the complete toolchain so that we have a clear idea of the role of each part and how to get from code to production. We start with a Git repository. We have, at Google, we have cloud source repositories for that, but you can use anything you like. And when you or your developer pushes to Git, you probably want to trigger some tests and build your container image. We have a product called Container Builder for that. That does actually much more than just building containers, but this is what it's why it's interesting to us today. Once the container image is built, you want to store it somewhere to be able to retrieve it and use it in production. We have container registry for that, and it comes with static vulnerability analysis of your containers, which is very, very important. Once the image is available, this is where Spinnaker arrives. It can take the image, run its deployment pipeline, and deploy it. It will deploy your container image on anything you like, but here we're interested with Kubernetes Engine. And finally, you have to monitor the whole thing, and you can use Stackdriver for that. The main point here that I want you to remember is that you can swap out each of these pieces independently and replace them with the tool that you like. If you use cloud platform products, you will benefit from all these integrations, but we don't want to lock you in, and we want you to be free of the tools that you are using. So this is all good, but you probably wonder what it looks like in real life. So let's do a small demo. in this demo, I will go over this part of the tool chain. I'm going to, so I have a sample applications that I'm going to show you. I'm going to introduce you to the Spinnaker interface, and I'm going to build a new container for this application with a small modification, and I'm going to trigger a deployment to Kubernetes with Spinnaker. So here we have the Google Cloud Platform console, and I'm on the Kubernetes engine page. You can see that I have a Spinnaker tutorial cluster that is spin up in the region Europe West 1B, which is Belgium. I have container registry, which is the product I talked about just a minute ago, where I can store my image. And here you can see that I have a couple of images already stored because I already deployed the version of my application. My application is very simple. This is what it looks like. It's basically a bunch of information about itself, where it's running, in which pod, on which node, in which version. And we have two different public IPs for those because I'm doing a canary deployment. The basics of a canary deployment is that when you want to deploy a new version of your application, you push it to a small fraction of your instances in production, you route a small fraction of your public traffic to those, and you can analyze how it's going. And if you're satisfied with that, you can push the new version of your application to the whole production system. So let's take a look at our pods. So this is the Cloud Shell console. And you can see that I have a bunch of pods that are already running. On the top here, you can see that I have some pods related to Spinnaker. We don't actually care about those today. This is just to actually run Spinnaker, and it's easier to do that in Kubernetes. And the ones that are of interest to us are the one at the bottom here. And you can see that I have 2 backend pods and 9 front-end pods. And in each of those, I have some production pods and some canary pods. If I take a look at my services, you can see at the end that I have 2 services of type load balancer with a public IP. And one of them is routing to our canary, and one of them is routing to both our production and canary pods. So let's take a look at Spinnaker now. So this is the Spinnaker interface, where each of these lines is a continuous deployment pipeline. So this is actually quite simple to understand. The first step is to deploy the canary version. Then we run some tests. The tests are very simple. We just check that the application is returning 200 OK HTTP code. And then Spinnaker is going to wait for human confirmation. And when it gets the human confirmation, it's going to deploy to the production. So if we take a look at our load balancers inside Spinnaker, this is what it looks like. You have a couple of internal load balancers for the backend, but the most important ones are here for the front end. In the canary load balancer, you have only the canary pods, and here you can see the public IP. And on the front end, you have both the canary and production pods, and here you have the public IP. So right now our application is orange, and we're going to make a small change to make it blue. Okay, I just have to change that into blue. And now I'm going to build the new version of my container by incrementing the version number. So this is actually quite fast because I cheated a little and I pre-built the container. So it's just Docker just needs to run the build. It doesn't need to fetch all the dependencies. So my container is built, and now I can push it to container registry. Same thing, this is actually quite fast because my new container is actually not very different from the old one, and only the two top layers of the container that are changed, and Docker only needs to update those. Sorry. So in container registry, if I hit refresh here, you can see that I have my new container. And if everything goes well, I should have a new continuous delivery pipeline spin up in Spinnaker right now. And you can see, yes, it's running. Okay, so it has detected my new version, and it's actually deploying it into Canary. So let's take a look at our pods again. And you can see that the Canary pods, the V5 here, is being created. So when the pod is in status container creating, it usually means that the Docker container is being downloaded by Kubernetes. And when those are running, the old Canary pods are being terminated, which you can see here. Okay, let's go back to Spinnaker. So this is going to be updated soon. And if we go back to our load balancers, you can see that now our Canary load balancers are pointing to the new version. So if I go back to my Canary load balancer and I hit refresh, now I have a blue application. Whereas if I go to the production load balancer, I have one chance in 9 to hit the new version of my application. Because on this load balancer, I have 8 production pods that are still on the old version and 1 Canary pod, which is in the new version. So we'll see if I hit the Canary pod or not. No, I stayed on the old version. So if I go back to my pipeline, so the Canary deployment went well. Then it did some tests, they went well too, and now it's waiting for my confirmation, and I can hit continue to push to production. In a few seconds, it's going to turn blue here. I hope. Yeah, so the deployment to production has started. And in a few seconds, we should see the new pods getting created inside Kubernetes. So on the back end, you can see my production pod being created. And on the front end, you can see that we have a bunch of new production pods that have already been created 7 seconds ago, while others are being terminated. So if I go back, so let's just wait a few seconds. Yeah, that's mostly fine. So if I go back to my production load balancer now, I hit the new version of my application. So that's all for the demonstration. Let's go back to the slides here. So a couple of take-home messages that I wanted you to have. Containers and Kubernetes are a great way to abstract your infrastructure, and they're a great way to package, ship, and run your application. And because Kubernetes is actually quite hard to manage, we think at Google that Kubernetes Engine is the best place to get a production Kubernetes cluster. On Spinnaker, this is a very useful tool because it makes your deployments easy, powerful, and observable. And by observable, I mean that you can very easily know which version of your application is deployed on which environment. And just to let you know, this presentation is based on our paper around Spinnaker and Kubernetes. So you can do everything I did during this presentation and much more by yourself by going to this URL. Thank you very much. And now let's go over to Q&A.
Thank you, Theo.
Thank you, Tom.
Brilliant.
Thank you.
And brave of you to do a live demo as well.
Yes, the gods were with me today.
Respect. We do have some questions coming in.
Yes.
I guess, where should we start? Oh, I like this one. I like Istio a lot. So tell me a little bit more. What's Istio and how does Istio fit into this then, Theo?
So Istio is an open source project that is basically a service mesh. So what is a service mesh? A service mesh is mainly used when you have a microservices architecture, but not only. And it's a way for you to easily connect your different services between each other and to manage a lot of things. So for instance, Istio will manage like retries and fallbacks and backoff and everything if there is a problem with some of your services. And it does authentication between the services also. And I think one of the most important features is the metrics that it exposes. So with Istio, you can know exactly how many requests one service does to another, how long they take, if the error rate or anything. And this is actually very, very important when you have microservice architecture. So right now, Istio is an open source project. Okay, it's not considered ready for production. Some people are using it in production, but it's like still pre 1.0. So
brave souls.
Exactly. But it's evolving fast, and we should look out for new advances on Istio because this is a very, very interesting project. Just one thing that I forgot about Istio, it also helps if you want to connect several clusters or one Kubernetes cluster with virtual machines that are not on the same place. It will connect everything seamlessly if needed.
Okay. Actually, on the topic of virtual machines, we had a question come in live asking containers versus virtual machines. How are containers better? When might you use a virtual machine, I guess?
So when you start in the world of containers, it's not obvious what are the advantages of containers versus virtual machines.
Okay.
But when you start playing around with them, you rapidly start to realize that they're much more fast, not performant, but they're much more fast to deploy, fast to download, fast to create, fast to destroy. So it actually improves your velocity on the infrastructure side, okay? And it's a few people are using VM images as a way to ship their application, but most people are using VM virtual machines that are not immutable. It means that when they need to publish a new version of their application, they're using the same virtual machines and updating their application inside the same virtual machines. You're not doing that with containers. With containers, you want a new version of your applications, you ship a new container that is brand new. And you don't change.
You don't go in and tinker with the insides of the container.
Well, you can, but you shouldn't do that. Yeah.
Yes. Okay.
And so containers are both a way to run your application and to ship it. And this is very, very powerful versus virtual machines. And of course, you can run them either on Google Cloud Platform or on premise or on virtual machines on-prem or everything. And it's exactly the same Docker image that you're going to use.
And when you're saying about that kind of speed of deployment and stuff like that, I guess that's quite important when it comes to CI/CD as well.
Yes, of course, because you probably don't want your developers sitting around for 2 hours waiting for their test to finish. This is actually one of the first use cases of Docker a few years ago, where people were using Docker containers to run their test very quickly from a brand new environment each time.
I used to be going to get a cup of coffee while code was compiling in my young day, but I guess now it's running tests potentially.
Well, now the problem is that people are doing so many tests that it takes as long as before. But
tests are good. We should have tests. Brilliant. So, crazy new world, lots of access, everybody's piling in, getting stuck in, but you don't want everybody doing everything. So how do you control access? Does Spinnaker allow you to restrict access, or is it a free-for-all?
So in the demonstration today, I had a very simple Spinnaker setup where I didn't have any authentication because it's just a demonstration.
Sure.
But you can plug it. You can plug Spinnaker to a different authentication system, such as Google Authentication, for instance, or GitHub if you want, and you can give you have access control lists inside Spinnaker that allow you to control who has access to what, depending on which group they are in outside of Spinnaker. So, for instance, if you have someone in the marketing group in Google Groups, you can just give them the right to push the continue push to production in the demonstration. So, everybody, so the developers push to Canary. And then it pings the marketing person, and the marketing goes, "Oh yeah, that seems fine. Let's go ahead," and they can push the button themselves. Or you can even give this right to your CEO if you're feeling like.
Why not? Yeah.
Yeah, exactly.
Awesome. And breaking, kind of stopping at that point and then having somebody different deploy to production, is that something you see as kind of a best practice or see commonly, or do people normally just have everybody push everything?
So it's a best practice, but I don't see it commonly.
There you go, folks. Room for improvement.
Because you probably want someone different to validate your application than the one that coded it, actually.
Right, that makes sense.
And if you push this idea to its furthest, you should have someone different pushing the push to production button at the end. And that's why I think it's a best practice. But in reality, it's often quite hard to implement, mostly because you probably want some people that are not used to very technical tools to do that in the end. And Spinnaker offers you like a very nice graphical user interface for that. And you can like open it up a little for that.
Brilliant, thank you. So another question's come in. So how does Spinnaker relate to Helm? In fact, could you just talk maybe about some of the common tools around? It's quite a big ecosystem of tools around Kubernetes.
Yes.
It's a pet subject of ours. Can you tell us a little bit about some of those, and Helm in particular?
Okay, so for the first part of the question, let's back up and tell what Helm is in the first place.
Cool.
So Helm is a package manager for Kubernetes. You can think of it as the apt-get of Kubernetes, and you have a whole lot of packages, they're called charts for Helm, that are pre-made by the community. And for instance, to deploy Spinnaker here today, I use the Helm package because this is very simple. Helm deploy Spinnaker, puff, I have a Spinnaker running inside my Kubernetes. And Helm is a great way to deploy your applications because you can put some parameters, some variables inside your configuration and everything, and use the same package for your dev environment, your production environment, and just change some parameters. So this is a very nice tool, but actually it doesn't work well today with Spinnaker. Okay, Spinnaker has its own way to deploy applications. Okay, and it doesn't use Helm. What's true is that there is a version 2 Kubernetes provider in Spinnaker that is currently being developed, and it's going to be much closer to the native Kubernetes ideas than it currently is. So it still won't use Helm, but you will be able to use a native Kubernetes templates. Okay. So some other tools around Kubernetes. Let me think. 1 second. So one tool that is often used for monitoring, for instance, is a tool called Prometheus, which is out of SoundCloud, I think, and it's a monitoring tool that is also based on the Google internals way of doing monitoring, and it's very well used and known today in the Kubernetes world. And the principles are very simple. Each application exposes an HTTP endpoint with a bunch of metrics, and Prometheus is going to poll those metrics periodically, and then you can just request some data out of Prometheus, and you typically use Grafana to do dashboard with Prometheus as a backend. And finally for logs, At Google Cloud Platform, we have Stackdriver logging that automatically gets all the logs from your containers inside Stackdriver logging, and you can search through them, etc. But often people are also using Elasticsearch for that. You don't actually need to on Google Cloud Platform, but if you have a Kubernetes cluster outside of GCP, you can use that.
So giving the ability to kind of run the same stack on-premise or in Google Cloud, or indeed, I guess, other clouds as well.
Yeah, exactly. Exactly. That's the whole point of Kubernetes, is for you to be able to run everything that you want the same way everywhere.
Brilliant. Thank you so much, Theo.
Thank you, Tom.
Brilliant.
Yeah. And back to the studio for the next session.
Thank you.
Thank you.